Welcome to another video. Today you will learn how to create a seismic susceptibility map in Arcgis Pro using 6 different variables, namely the lithology of the terrain, the density of earthquakes, magnitude and the depth of the earthquakes, and the distance and density of the geological faults. In this tutorial we will use several super interesting tools, such as kernel density, YDW, Euclidean distance, and Raster calculator, for example. After we have all the variables created, we will normalize all the elements on a scale of 0 to 100, using several different formulas. So, without further ado, let's get to the video. Okay, so let's start the video by opening Arcgis Pro, then create or click on Map, give a name to your project, I will call it Earthquakes, and then click on this folder icon and save it to a folder of your choice. I will choose this one in my desktop and then just click OK. Now the first thing I'm going to do in Arcgis Pro is click on this icon to add folder connection, then just select your folder and click OK, and this will help us to reach our folder easily. So you just click on your folder and I will import these 4 shapefiles, so the earthquakes from the year 2000 to 2024, the area of interest of this video, the Spain country, the faults, geological faults of Spain, and as well the geology and lithology of Spain. So I'll select them all and import them to the project. Now for the next step, I'm going to change the coordinate system of all the shapefiles, since this map is in WGS 84 and I want to work using a Spain coordinate system. So to do this, just click on Map and click on Properties, then right here go to Coordinate Systems, and in this case I will select this one, Madrid 1870, and I will click OK. Okay, there we have. Now we have the Madrid coordinate system. Now let's open the attribute table of the earthquake shapefile, and as you can see we have the event ID, the hour, the latitude and longitude, the depth of the earthquakes, the intensity, the magnitude type, and as well the localization. So what we are going to use in this video is the depth and the magnitude. Now if we check the geological faults, we can see a bunch of data, but in this case we are only going to use the geometry, so we are not going to use any field of this shapefile. In the lithology, we are going to use this field right here, the lithology. This is in Spanish, but I will share with you an Excel file with this lithology in English, and to finish the area of interest, so the Spanish mainland country. So the first step I'm going to do is unselect all these shapefiles, and since we are only going to work with the mainland Spain, we need to delete these islands. So since we have the geology of these islands, the thing I'm going to do is go to Map, then click on Select, then drag a rectangle in these islands, and on your keyboard just click on Delete to delete these islands. Now a thing that I like to do when I'm working with rasters and spatial analysis tools is creating a raster mask, And so to do this, I will use the Spain shapefile to do a mask. So to do this, go to Analysis, then go to More Tools and search for this tool right here, Polygon to Raster. Click on Polygon to Raster, then drag and drop this shapefile into the input features. The value field can be the default value. Right here on the output, I'll save this folder, select this folder and give the name of es_mask. Then for the cell size will be 500. I will use 500 meters as a cell size to each and every one of the data that I'm going to create. Then right here just select the output coordinate system, the extent, and click on Run. Now let's wait a second. Okay, so there we have our mask. Let me place it on top so you can see the mask. And now we can do the first analysis. So the first analysis will be on the earthquake shapefile. So once again go to Analysis, click on this arrow, then More Tools, and search for this tool right here, Kernel Density. So click on Kernel Density, drag the earthquakes into the input point or polyline features. Population field will be the default value. Now select the output. I will call it, for example, KD_earthquakes. Okay, it looks like the name is too big, so I will change earthquakes to quakes, for example. Okay, once again the cell size will be 500. We don't need to change anything more right here. For the environments, coordinate system will be the Madrid coordinate system. Extent will be the Spain shapefile. Mask will be the mask that we already create, and snap raster will be the mask as well. Okay, now we can click on the Run button. Okay, there we have. Now what I like to do, and the step that I'm going to do always will be to change the symbology so we can compare the results. So I will go to the symbology, then change this to stretch, and I will choose a color scheme from green values to red values. So the green color for the lower values and the red color for higher values. And as you can see right here on the south of Spain, we have the higher density of earthquakes. And if I select the earthquakes once again, we can see that the result represents the reality very well. We can unselect the kernel density once again, and now we can move on to the next tool. Click once again on More Tools, and now just search for IDW. Click on IDW, drag the earthquakes once again to the input point features. This time for the value field we will choose, for example, the magnitude. So let me open the attribute table of the earthquakes once again, and we can see that we have the depth, but then we have the magnitude as well. And this time we will select the magnitude to do this analysis. So select the magnitude, change the cell size to 500 once again, do the same process to the environments. For the mask will be the mask, snap raster the mask as well. Click Run. There we go. Now let me change the symbology once again from classify to stretch, choose the same color ramp, let's wait a second, and if we check this map we can see that in the red color or orange colors we have areas where happened earthquakes with higher magnitudes, and in greens earthquakes with lower magnitudes. So now let's go to analysis, more tools once again, YDW once again. Now let's represent the earthquakes by depth level. For example, if we open our attribute table, here we can see that the largest earthquake is 6.2 magnitude, but having happened at such a high depth, so 623 kilometers, the intensity at the surface ends up being attenuated. So I just noticed that I forgot to give the magnitude IDW name. I'll change it shortly. Let me change the Z value field to this one. This is the depth. Let me give it a name. I will call it YDW, for example, underscore depth. Cell size will be 500 once again. Coordinate system, same as current map. The span shapefile as the accent and the mask as the mask and snap raster. Let's click on run and wait a second. Okay, let me change the color ramp. Change this to stretch, this color ramp, and as we can see, it's here in the south of Spain that we have the cartographic representation of deeper earthquakes. But what I'm going to do now is to invert our color map. There is represent the smallest depth in red and the greatest depth in greens. Now let me export the magnitude once again, because I forgot to change this name right here. So let's click with the right click, then data, and then export raster. Right here I will just change this output folder. Let me call it ydw1 underscore meg. Select the folder first, save, and export. Okay, there we go. Now we can remove this one. Now let me change this color ramp. Okay, just change this to this one. Okay, and now we can move on to the next step. So now what we are going to do the analysis is on the geological faults. So the earthquakes right here, we are not going to use them anymore. But now we are going to do the analysis on this one, on this shapefile. Let me just increase and change the color of these geological faults, maybe to black, and increase the size to 2. And there we go. We can see right here on the south that we have a lot of density of faults, and it has a correlation with the earthquakes. As you can see, we have a lot of earthquakes right there on the south as well. So therefore we will start by representing the distance between faults. there is smaller distance between the different geological faults will have a greater weight, and greater distance will have less weight in the final analysis of our map. So just search for the Euclidean distance tool, drag and drop the fault right here on the input raster or feature source data. So just drag it and drop it right here. I will call it, for example, KD underscore faults, ED underscore faults. We don't need to change nothing right here. For the cell size, once again, will be 500. Then on the environments, for the coordinate system will be the Madrid one. Right here, the Spanish mainland shapefile. And for the mask and snap raster will be our mask. Now let's click on the run button. So in this result we have to do the same as we did in the previous result. So that is geological fault with smaller distance between them will have to acquire greater weight in our final analysis. And to visualize that, we just need to select our color ramp, and then right there we just need to invert the values, so we can see that right here on the south we have a green color, but we want in this case the red color. So right there on the symbology, just check mark this invert, and we can see where we have the lower distances between geological faults. The next step is to do the analysis of the density of faults. So we are going to represent on the map the places where we have higher density of geological faults. So just search for kernel density, drag and drop the faults right here. Then just change the output raster. I will call it KD underscore faults. I'll click save. Output cell size will be 500 once again. Then on the environments we just do the same process. Okay, let me change the symbology of these results as well. And we already can see that the density of faults are higher right there on the south, as was expected. So let me change to this one. Here we go. And this time we want the red values to be right here. So we don't need to invert this color ramp. Let's now open an Excel that I will also share in the link in the description. This link refers to the different types of lithology in Spain, and also has the different propagation speeds of seismic waves in each of the different types of lithology of Spain country. That is, for our analysis, we will mention that higher propagation speeds will have a greater impact and lower speeds will have smaller impact. So let me maximize this Excel file. As you can see, we have the lithology right here. This is the same as we have on the attribute table, but now in English. We have this symbology right there to join the different tables, the type of rock, and then the speeds of each seismic wave propagation. So this value is on meters per second. Then on the right we have a little representation of the speeds of each rock type. So what we are going to do is just select this data into Arcgis Pro, and then to each variable we will do a ponderation. So in this case, the velocity in meters per second. Let's start by opening the geology attribute table. as we can see here, we have this field referring to the lithology, but in Spanish, and we also have this field right here with the code that we will use to join both tables. We could easily join the two tables, but as there are few values, we can use the select by attribute tools to update the attributes in Arcgis. So the first thing we are going to do is add a new field. So just click right here on this add button. I will call it speed, and the data type will be double. And then we just need to fill each row with the speed value that we have on our Excel. Let me drag this to the left to be side by side with our Excel file. Then go to Map. Click right here on Select by Attributes. And then we just do this. So the input row is the geology, and then we just need to say that lithology, or in this case the symbology of the lithology, is equal to, for example, TL1. Click on Apply. Move this to the right. Then right click, calculate field, and we need to say that speed is equal to, in this case, 1300. So just type 1300 right here on this box, click OK. Let's unselect all these values. Then we can go to the next one, for example, TL2. Okay, this is the TL2, as you can see. Now right click once again and just click on calculate fields, but this time the value will be 1400. Click OK, and then you just do this to each one of the lithology. But there's actually a fastest way to do this. So you can select multiple values at once. So for example, let me think, maybe we can select all the lithology that has a velocity of 1500, for example. Just search for where symbology of the lithology is equal to TL3, then click R and you do the same process, so symbology, and then we can select, for example, this one right here, TL13. Then the TL14. HOR. And then the TL15. 16 as well. Then 17. And the last one is this gravel conglomerate, sand and silt, the TL22. So it's the TL22. Click OK. Once again, right click on the speed, go to calculate field and just type 1500, and you can click OK to apply the result. And you just do this to each one of the lithology and rock type. Okay, now that we have all the values of the speed represented in our shapefile, search for polygon to raster to change this shapefile into a raster. Drag and drop the geology right here. The value field will be the speed. Then just give a name to this raster. I will call it PR_speed, for example. Click Save. Click Save. The cell size will be 500 once again. And for the environment, we do the same. So just repeat the process right here. Snap raster is mask and click Run. Okay, I just made a rookie mistake. So we just have the representation of the areas that are selected. So we just need to click right here on clear. As you can see, we have these values selected. Just click there to unselect and repeat the process. And now we have all the values represented in our raster. We can see that in blue we have the highest propagation speed of seismic waves, and in violet we have the lowest speeds. Now we can remove all shapefiles from our project, and here, as we have already seen, the higher propagation speed, the greater the seismic susceptibility, and the lower the speed, the lower the seismic susceptibility. We now have a problem here, which is actually not really a problem, but which we have to solve. That is, if we notice, for example, here in the speed of the seismic waves, we have values between 1300 and 1400. But if we look at other rasters where values are much lower, some around 0, it's difficult to do a mathematical operation with low and high values. That is, if we have to normalize all the data to the same scale. So, in other words, what we are going to do now is normalize all the rasters created so far on a scale of 0 to 100, where 0 will have the lowest weight in the final analysis and 100 will have the highest weight. As we saw a moment ago, there are two results in which we had to invert the color ramp, the depth and the distance between geological faults. So, in other words, now when we do the standardization, we must be aware that these two elements will have to be normalized in a different way compared to all the others. So, what I'm going to do is to just group these two results and call it min. And then I will just select the rest of the elements in a group and call it, for example, max. Actually, let me change the name to be easier to understand. So in this case, I will call it maybe low values, more susceptibility, and this one, higher values, more susceptibility. I think this way is easy to understand. To normalize these values, we will use the Raster calculator tool. So, to use it, just go to Analysis, click on this arrow, More Tools once again, and search for Raster calculator. And we will do two different expressions. The first one will be raster minus raster dot maximum value. So you type dot maximum, close parenthesis, then divide, open parenthesis, raster dot minimum value, so just type dot minimum, minus raster dot maximum, close parenthesis, and then multiply by 100 to have the values between 0 and 100. So this time we have values between 0 and this large number, but with this formula we will convert these values between 0 and 100. So just select your output. For the environment, just do the same process, and this formula is used for the distance between faults and for the depth as well. Click Run, and there you can see we have values between 0 and 100. So if we select this color ramp, we can see that now we have 100 right here on the south, and we don't need to invert because this formula did this for us automatically. So now for the depth we just need to do the same step. Let me remove this one, go to analysis once again and search for or just click on Raster calculator. And now we do the same formula, but this time for the depth. So we need to convert these values again to 0 to 100. Just open parentheses, then you say that depth minus depth dot maximum, close parentheses, then divide and open parentheses, depth dot minimum minus depth dot maximum, close parentheses, and multiply by 100 once again. Let's call it RC YDW underscore depth, click save, and once again this time we will have the values near 100 to the lower depth and values near 0 on the higher depth. So it will be the opposite of the first result of the depth. Let me select this color ramp again, and as you can see the result is now correct and we don't need to invert the values. Now we need to move on to the other formula, these ones right here. So this time the lower values will have or actually the opposite, this time the higher values will have more susceptibility, so we do the formula in a little different way. So this time what we are going to do is open parentheses once again. We can start with the speed of seismic waves. So open parentheses, then you say that speed, but this time will be dot, actually a minus, and then speed dot minimum. So in the previous we typed maximum right here, but this time is minimum. Then divide open parentheses by speed, and this time dot maximum minus speed dot minimum, and then close parentheses and multiply by 100. So actually this formula is the opposite of the previous one. So let me call it RC speed, for example. Click save and select your environments once again, and let's let's see the result of this formula. Okay, there we go. So let's see. So the lower values are with the violet color. So it needs to have darker values, and it seems that is correct. And now we just do this for the three other rasters. So we can actually remove this one. And this time I'm just going to double click on the faults this time. This one. Now I will just cut. Let me Control Z. Actually, we cannot cut. I will just Control C to copy. And then I will just replace these rasters for this one. Since the formula is exactly the same, we just need to change these names in red. Like this. Then I will change the name to RC_KD_fault. The environments are the same, and we can click Run. Okay. Now we can remove the faults. And now we can do the same formula for this time for the magnitude. I will do the same. I will just copy to here. Then just remove it from here and replace all these reds, but now with the YDW magnitude. So just replace these ones, this one as well. Don't forget to change the name, so you don't replace the previous with this one. So just call it RCIDW_mag. Click Run to represent the magnitudes on a scale of 0 to 100. And now we just can actually you can see that the results are correct. And to finish, we just need to do the same steps, but this time for the density of earthquakes. Once again, just select your earthquakes and just replace it with the magnitudes right here on these formulas. This one as well. Let me change the name, for example, to RC_KD_quakes and click Run. Now that we have all the values normalized on the same scale, we can create our seismic susceptibility map. In this example, I will just add all the variables and add all the variables together, but in the next week's video I will show how we can improve this analysis using different weights for each variable using the analytic hierarchy process method. So to do this final analysis, just go to Analysis once again and search for the raster calculator again. And now we just simply will just do a sum between the 6 variables. So the density of our earthquakes plus the YDW of the magnitude plus the density of geological faults plus the speed of seismic waves in different lithologies, plus the YDW of depth, plus the distance of geological faults as well. Let me call it some variables quakes. Okay, the name is too big again. Let me just call it sum underscore var. Do the same steps for the environments, for the mask and snap raster as well, and click on the run button. Now we could normalize these values again, for example on a scale of 1 to 5, but in this case we'll just represent the map using the classification in 5 quantiles. So we just need to do this on the symbology panel, but first let me change this color ramp to see this result. So let's just search for the same color ramp, this one right here, and we can see that right there on the south we have the highest seismic susceptibility, for example. But now what I want to do is to normalize this in quantiles. To do this, change this from stretch to classify. I will change the color scheme once again. This one. And change the method from natural breaks into quantile. This one. And define 5 classes. And there we go, the normalization in quantiles. And now, for example, we can change the labels right here, for example, to this one to very low susceptibility, this one to low, this yellow one to medium, this orange to high, and the last one to very high, for example. For this video, that's all. In the next one we will take this result again and apply the analytic hierarchy process method to define different weights. And after we have the map finalized, we will create a layout to have a complete representation of this map. Thank you for watching. If you like this type of content, don't forget to like, subscribe and comment what you want to learn next.